Hello, I'm Matthew Venn. I'm the Chief Sales Officer for Yosis HQ, a science communicator and electronic engineer. And I'd like to say thanks to Derek for asking me to do a keynote for GNU Radio Conference 2021. So let's get started by talking about who we are at Yosis HQ. Yosis HQ is the place for open source EDA. We do synthesis, place and route, and verification. We create and maintain Yosis, NextPNR, and related tools. We want to increase access to state-of-the-art EDA design and formal verification tools. We have an open source version and a paid-for version that adds System Verilog, VHDL, and System Verilog assertions language support. Feel free to get in touch with me if you want a demo. We also offer support and do custom projects if you need any of the tools extending. The main thing I want to focus in this talk is about the state-of-the-art of the open source FPGA tooling. Derek said that a lot of people here will be familiar with FPGAs and FPGA development, but mostly using the proprietary tools. So I want to give you an update into where we are with the open source tools. So what exactly do we have inside an FPGA toolchain? We want to be able to write our design. We need various types of language support. We have verification, for example, simulation, formal, coverage. We probably want to have some support for reusing intellectual property. We probably want to have some frameworks for easily building systems together rather than having to type everything out. System on chip generators. We need synthesis tools, so that's where Yosis comes in. For FPGAs, we want to do place and route, and that means we need to know about where things are in different devices and know how they're programmed. Let's get a little bit of context here. A lot has happened very quickly. So Yosis was originally created by Claire Wolf back in 2013. But at that time, there weren't really any FPGA targets that we could use it for. So it was mostly useful for academic purposes. Later on, Claire reverse engineered the Lattice ICE40 family of FPGAs as part of Project Ice Storm in 2018. And that really marked the beginning of a flourishing era for the open source FPGA ecosystem. NextPNR came along. We saw an explosion of cheap dev boards based on the Lattice parts as they were the most supported. Then we had the ECP5 family reverse engineered, which is a more powerful family from Lattice. Lattice now showcases various open source boards on their own website. And of course, work is always ongoing, fixing bugs and improving quality of results. Our CTO at Yosis HQ is Claire Wolf, and she was able to take a few minutes out of her busy schedule to talk to us about her involvement. I didn't want to get too far into the details because she recently did a very technical talk with the Open Source FPGA Foundation. So you can check the link to find out more about that. So just checking my dates, Yosis started in 2013?
I think I started working on it in 2011.
Okay.
Originally under a different name, which was just like a ridiculous, unpronounceable acronym, but I was sure it would not show up as part of anything else, so I could easily search and replace it when I would come up with the real name, which was Yosis. And it was part of my work for my bachelor's thesis. So I was working on a project with coarse-grained reconfigurable hardware, and we had to figure out a way of getting designs into our custom flow. And I looked at the solutions that existed and decided we would need to build something. Yeah.
From simple beginnings.
Yeah.
Yeah. So was that like the start of your EDA tooling journey?
Not really. I have no idea when this was, maybe 2005, around 2005-ish. I was playing around with the custom synthesis flow for simple FPGA architectures. And at the time, I was trying to convince FPGA vendors to open up the bitstream documentation so that it would be possible to build an open source flow. At the time, I was looking at the synthesis part of Icarus Verilog for design entry. But yeah, essentially all the vendors I contacted told me that it wouldn't make a difference if they would open up the bitstream documentations, because nobody would be able to build tools for them anyway, because it would be like far too complicated. So yeah, and about 5 years later, I just decided to write the tool that nobody could build, apparently.
And you've continued on that stint now, so EDA tooling is kind of your main interest now, is that right?
Yeah. I mean, it's a broad field, right? So we do a lot of stuff with formal verification. So with this comes like constraint solving and SAT and SMT and all that kind of stuff. And then a lot of other software engineering problems that are like interesting things to dive in on their own right? So, but it all like ties together to this EDA universe.
So then let's just jump to Pico RV32, which I know isn't your favorite subject.
Yeah.
Did you ever expect to see that on so many taped out microchips synthesized using your own synthesis tool?
Oh God, no. So when I first learned about RISC-V, I thought, "Ooh, this is really, really neat and nice." I've been building small custom processors for various system management tasks at my day job at the time. And usually building such a small processor is relatively easy and straightforward, but building the software tool chain that supports it is like a lot of work. So I was pretty excited about RISC-V, primarily because it meant that there was an existing tool chain and I only would need to build the processor. And more or less just to like get to know the ISA a bit, I decided to write a small processor. My design goals at the time, because in my day job I was working with the Xilinx tools to optimize it for that. And my optimization goals were only area and frequency, but not performance. So it's a horrible design. I'm so embarrassed that like I I wrote really nice like compute accelerators that nobody will ever see because they're like part of that commercial endeavor. But that this is the piece of HDL code that I wrote that is like most popular is a little bit embarrassing. But I think it also shows that people have different priorities, and sometimes it's easy to optimize for priorities that don't actually fit the needs of a lot of people, just because it's, for example, it's a much nicer and cleaner engineering problem to build like a pipelined and superscalar processor. But when you have something like RISC-V, where different people can try out different things, then sometimes someone hits a nerve, and we would not have a solution that would sit in this specific corner of the design space if there would not be this freedom to just experiment with stuff.
So the last question I've got for you is, as the CTO of Yosis HQ, what's on your roadmap for the future?
We accumulated a lot of technical debt in the last decade, which I still think was necessary because we needed something that works end to end in order to get get this movement started and get people involved. All of this is much easier if you have something that's already useful and that works for at least some applications. And then we've just built on that and extended it. And now we are at a point where there are certain things that we would want to support much better in our tools, but the architecture that is now 10 years old and has accumulated a lot of technical debt is not really fit for the purpose. So with Yosis HQ, we hope that we will be able to get the resources and the time to be able to refactor those parts that need refactoring in order to push forward. And so I think this is something where maybe in the next 2 years or so, we will hopefully be able to release a couple of very, very interesting new things.
Cool. Well, thanks very much for making time to talk with me, Claire.
Yeah, you're welcome.
What kind of technical talk would be complete without a demo? So instead of doing the normal Blinky demo, I decided to do a RISC-V Blinky demo, as that would push things a little bit further and also showcases just how quick the tools are in doing these kinds of designs. And for this demo, I'm happy to show off my own FPGA dev board that I built around the Lattice ECP5 part. I'll start off by cleaning everything up, and then we'll run the flow with the makefile. And this starts off with Yosis doing the synthesis. Let's take a look at the stats of this demo and the final results. So it's using the 45K ECP5 on my dev board. That's registered OSHW. We're using the Pico RV32 RISC-V CPU by Claire Wolf with some wishbone LEDs and a serial terminal, reading firmware from Flash. The firmware is compiled with GCC. The bit stream is ready in 45 seconds, so that's synthesis and place and route. In this case, the programming is a bit slow. We get an Fmax of 56 megahertz using 20% of the available logic elements. And this ECP5 has 72 hard multiply accumulates, so it could be a good target for radio applications. Copy it over to the Raspberry Pi. And then I sped up this part of the video because programming is normally a lot faster, but this is bit banging from the Raspberry Pi. It takes a little while. So now we've got our RISC-V Blinky, log into the Pi, open a serial terminal, and then show the GRCon banner. At Yosis HQ, the fundamental tool is Yosis, the synthesis tool, and this is forming the core of many other different flows. But there's also a lot of other important tooling, and I want to highlight some of these in this talk. So we have verification tooling and intellectual property, and Yosis HQ provides formal verification with a tool called SBY. We have simulation tools and frameworks. Kokotb is a really interesting one. I'll talk a little bit more about Kokotb in a minute. We've got a couple of other simulators, Icarus and Verilator, and a new one called CXXRTL that's built into Yosis, and it's only been going a few years, but it's already got very impressive speed results. We've got GTK Wave and a new tool called VCDROM, which is a cloud-based VCD viewer. And then we have design frameworks and package management. Litex is an infrastructure to create FPGA cores and SoCs. FuseSock aims to increase reuse of IP. And SymbiFlow aims to be the GCC of FPGAs, and is also the best bet if you want to be trying out Xilinx devices. So let's pick on a few of these and look at them in slightly more detail. One of my favorites is Kokotb. Kokotb is a bit like UVM, but it's all Python based. It supports a wide range of simulators. You can just plug those in, even commercial ones. And it's got some bus protocols broken out into a different Python module that supports some common bus protocols like AXI, Avalon, and Wishbone. It's got out-of-the-box CI support, which is great for getting your hardware in CI. And it lets you do cool stuff like attaching your FPGA design to your real local network. That's one of the examples in the tutorial. And this is a little demo that I wrote a while back that can read a WAV file, run it through a filter in the FPGA, and then write back the WAV file. So that shows how much nicer it is doing this with Python than trying to do the same thing in Verilog. CXX-RTL is a new simulator built into Yosis, written by Whitequark. It's fairly similar to Verilator in that you have a single C++ include file that you then compile and you can run your design. Performance keeps on improving. Definitely one to keep an eye on. Litex is a system-on-chip builder. It lets you easily build things like bridges, PCI connectors, connecting to various types of other hardware. And there's been some very impressive projects put together with this. Florent, the maintainer, is building FPGA SDR systems for his clients. Those aren't open source, but Litex is open source and is a very convenient way of building up complicated system-on-chip packages without a lot of effort. Most of the demos running Linux on FPGAs using the open source toolchain have been built with Litex. So now let's take a look at some example projects that leverage the power of the open source tools and see what people build with them. I'll kick off with Eric Brombauer's SDR. This is a fairly old project, but it's one of the few that I've seen that actually implement the whole SDR on the FPGA. Slyvain TNT Munaut has shown just how much you can squeeze onto these small devices by porting Doom to an UP5K FPGA, and also put together a great video if you want to find out the subtleties of how you can do this kind of thing. Esden at 1bit Squared has been working with the Glasgow community. Glasgow is a development board designed by Whitequark, and it's a digital interface explorer, recently funded on Crowd Supply. The thing that I find most impressive about Glasgow is how you can install all the tooling extremely easily and quickly, and then you load on your different types of applets which provide the functionality, and those are synthesized as you need them. So this is a great example of doing something that would be much harder to do with the proprietary tools, where even just starting the tools can take 10 minutes. With this, you can choose the interface that you want, synthesize it, build a bitstream, and load it on all within seconds. I asked around for examples of SDR projects using the open source tooling, and Mike Walters, working with Great Scott Gadgets, has done some interesting integration with GNU Radio, targeting Luna, a development board for analyzing and hacking USB devices. Another SDR project, this one uses the ICE40, fits on top of a Raspberry Pi Zero, and gives you an SDR. So how do the open source tools hold up against the competition? It's a good question, and the Symbiflow team have a good tool that is tracking the different performances of the different combinations of tool chains and boards. And this one is showing a simple RISC-V core called Pico RV32, written by Claire Wolf a few years back. So I encourage you to take a closer look at these graphs if you want to find out more. One thing to note is that the ICE40 is a fairly low-powered FPGA, so most of those lines at the bottom there are on ICE40, and then the lines at the top are running on more powerful Xilinx faster FPGAs. I wanted to get the insights from one of the key open source FPGA developers, and luckily for us, Gatecat was willing to share their thoughts. I started off by asking their opinion on the suitability of the open source FPGA tools for the types of applications we'll see for GNU Radio. Also, just to note that their video drops out after a few minutes. One of your comments was that you think that a lot of the GNU Radio stuff is too big for NextPNR. Could you explain a bit what you mean by that?
Yeah, so I've heard, I mean, admittedly, it's not actually something I've looked into very much, but from talking to people about it, I've heard some of the projects, particularly the more complex stuff like RF NOC. We're talking about things like 300, 400K LUT, Kintex 7s that are being pushed to the limit. And even though there are theoretical pathways to play with those devices in NextPNR, they're currently highly experimental. The fact that Vivado is being pushed to its limit with those kind of designs makes me think that NextPNR really is going to struggle, because NextPNR on those sort of size devices is still very experimental. One of my big ongoing projects is to improve performance. For example, making the placer take rootability into account, so it places the designs in ways that are easier to root, because otherwise when you start getting big complex designs like that, it will appear to place them successfully, but then it won't be able to root them. So yeah, partly just that NextPNR simply hasn't been very well tested on such scale designs, because the most stable complete flow has been for the ECP5, and that's also the large device that NextPNR has been tested on most. It hasn't really been tested on devices beyond that scale very much.
And as you mentioned before, the biggest in the ECP5 family was 85,000 logic elements.
That's right.
Yeah. So you've also been doing some work on the Xilinx Open FPGA tooling as well. Is that called RapidWrite?
So RapidWrite is a project by Xilinx themselves, in fact, to provide a more open interface to their toolchains. Now, the important downside you have to be aware of that is that it does mean you still need to use Vivado to do bitstream generation. Of course, the advantage of that, if you're working with some big expensive FPGAs, Vivado will also do a bunch of design rule checks. So if you go through RapidWrite, you're also guaranteed that you're not going to get a bad bitstream that could potentially damage your FPGA, although the chances of that happening are still fairly low. I can certainly understand people are much more worried about that with a multi-thousand-pound FPGA than with a £100 FPGA.
Yeah. Have you ever damaged an FPGA with a bad bitstream?
No. It's one of those things that there's a lot of mythology about, but in practice, it's much harder to achieve than you might think. I know, I think at least one person has managed to do it on purpose, but that was very much a deliberate thing rather than something that happened accidentally.
Litex sounds like it's going to be like quite a crucial component in this whole flow.
Certainly, it does seem like the best source of getting these large complex IP cores. So I think Litex provides PCI Express, DDR memory, including DDR4, and I believe there's also a JESD204B core, which is very useful when you've got fast DACs and ADCs that you need to interface.
The question about, are there ways of abstracting interfaces to make it easier to integrate FPGAs into SDR frameworks? And I think NMyGen and MyGen and Litex, this is all kind of related there, isn't it?
Yeah, so I think probably the best project to look at here as a reference point would be White Quark's Glasgow, because she's worked very hard on deeply integrating NMyGen into Glasgow. So the fact that there's an FPGA toolchain sitting behind there is largely abstracted, particularly as it can support the WASM builds of Yosis and NextPNR, which sounds like it might be slow, but actually the overhead of WASM is very low, and it means that both Yosis and NextPNR can be installed as Python packages. So the end result is that installing the Glasgow toolchain gets you NMyGen, FPGA toolchain, basically everything hidden behind a kind of very nice command line interface to the point you really don't even know there's an FPGA in there.
And one of the great things about the Glasgow board and all that software support is you write your little applet in NMyGen, and then everything is synthesized to a bit stream that then gets run on the board, which might sound for people who are used to kind of classical FPGAs would take a long time. But one of the nice things about this project is that's actually a very fast flow.
Yeah, and when you're looking at bigger FPGAs, and this can be done both with the Xilinx tools and hopefully in the future with open source tooling as well. The trick here is often to make a kind of shell, essentially part of your design that doesn't change, that contains the interfacing, the PCI Express, maybe some parts of the radio signal path that are not changing very often, ADC interface, all those kind of things. And then the part of logic that you replace is just the blocks that you want to replace using partial reconfiguration. So you don't have to do a full design rebuild every time things change. You can just reload that part of the device. And this is definitely something I want to experiment with, because it's also one of the ways of making open source tooling more approachable on large FPGAs. So yeah, targeting a region of some large ultra-scale FPGAs is on my to-do list. Perhaps not for this year, but certainly for next year.
Sounds like a long to-do list.
It really is, yes. I think that unfortunately applies to all of us working on open source FPGA tooling.
Great. Okay, well, thanks very much for your time, Gatecat. I really appreciate it, and hope you have a great rest of your day.
Thanks. Very, very nice to speak to everyone here.
To get a better understanding of the pros and cons of the open source FPGA tools from a developer's perspective, I was lucky to be able to speak with TNT, who did the Doom example, and we had a little chat about his experience. Yeah, so I was wondering if you could speak a little bit to the difference between the open source tools and the industry tools.
Okay. So I mean, obviously the big difference is, I think, the convenience of um getting started and just getting the stuff up and running. It can be a big stop. Just it's small things that in the grand scheme of things are not necessarily super important. But like recently I had to upgrade Vivado. That means, okay, I need to download like 80 gigabytes of install files, and then I need another 80 gigabytes to actually install them. Which if you try to do that like on the laptop, that's 160 gigabytes. That's not a small part. And then you sometimes need to have 3 different versions of the toolchain, because um, the reference design from ADI, for instance, they work on a very specific version. They require a very specific version of Vivado. Then you want to synthesize code for the Etus USRPs. Again, they're designed to work on a very specific version of Vivado, and that's not necessarily the same one. So that's easily gets a bit annoying, and it's it's not a huge deal, but it's one thing that's definitely an inconvenience. Then you have the licensing, because you need some of them, even if the license is free, you need a license file, and that can be very annoying. There are several cases with Lattice, for instance, using either IceCube or Radiant. Their license request processing seem to have some manual step in them, which means that when you request a license, you need to actually wait for somebody to accept it. And I remember at the last CCC I was at, like I needed a license because the one I had expired, and it's CCC. It's like between Christmas and New Year, nobody was processing requests. I just couldn't get a license. That kind of stuff. That's the first thing. And the other, I think, is mostly the way you deal with problems and issues and things like that. It's actually something that happened very recently. That is a very similar case that happened both with a closed toolchain and with the open toolchain. So like with the open toolchain, I was trying to update the design of the Academy badge and run it on the recent toolchain, right? And I ran into a synthesis issue, like a synthesis bug. That doesn't happen often, but sometimes what the toolchain produces as a bit file is doesn't actually implement the logic that you described in your Verilog, right? And it took me some time to trace that back to the actual problem that one turned out to be in users itself. It happened in like very specific set of circumstances, but I was able to dig pretty far into isolating the problem, submitting it to GitHub in this case, and I think like in less than 24 hours after I fully described the problem, um, that that was solved, and I was able to update users and be fixed. And something very similar on even the same platform. Oh no, that was on Ice40. The Academy batch was ECP5, and then I had a problem. I was porting a design from IceCube 2 to Radiant, the new Lattice tool. And again, like the design wasn't working. It worked fine in IceCube 2. I ported it to Radiant, and it doesn't work on hardware. And after several days of tracking it down, I finally managed to isolate it to an actual synthesis bug as well. Like the logic that I described in Verilog got part of the state machine got optimized out, which it shouldn't have been. And just first reporting the issue is like Lattice as a text service request, I think it's called, but you need an account on Lattice. That account needs to be verified. For some reason, every time I create an account, it gets deactivated after some time, and I need to create a new one. So now I think I have like 5 accounts with Lattice. And so I submitted the TSR. It already takes several days, I think close to a week and a half of back and forth, just for the engineer to understand what the problem is, and that I'm not an idiot and I didn't open an issue for nothing, right? And I did send actual bug in the tool, and then it finally gets escalated like a week later to the software team, which confirms the issue. But in the end, okay, yeah, we have a bug, but you have a workaround, and we don't currently have the time to fix it. So issue closed, we'll fix it when we can, right? But in the meantime, even though I isolated the issue, first, I don't have a fix. I wasn't able to look at the source code or anything to know exactly what precise set of circumstances triggered that bug. So I don't know if I'm going to hit it again or not. And so that's kind of a very frustrating experience in general. And that's really what I like with the open source tool, is the able to dig. When I hit an issue, is be able to dig into it.
So that's some of the positives. Now give us some of the negatives.
Well, I mean, so the negatives so far, the reason I say why, currently I only use the open toolchain for ICE40 and for ECP5. I don't use it for Xilinx. Some of the negative, the one I hit the most often is the lack of I/O timing analysis, because that's something that exists on ICE40, exists in ECP5, is that the toolchain doesn't provide you, when you want to get signal in and off the chips, right? You have to obey the setup and hold times of the flip-flops that your signal is coming out of. And so you have the clock to out for your outputs, and you have the setup and hold time requirements for your inputs. Currently, that just doesn't exist in XPNR at all. So the way I basically work around that is that every time I have critical timings, I use the I/O registers, which provides me with deterministic timing, meaning that they're kind of always the same. And so I extracted them once from IceCube, and I have them on a text file, and I just basically use that and do the timing on paper, the timing analysis myself on paper every time I need to do it, basically. And the other limitation is kind of related, because it's also in timing analysis that you can't, like, advanced constraining is not possible at the moment. So you don't have things like multi-cycle constraint, tell the tool, okay, this signal isn't going to change, it's only going to change once every 2 cycles. So you actually have 2 clock periods for that particular path. Or, okay, this signal that goes from that clock domain to that clock domain, I want to have a min or max delay constraint when you do cross clock stuff. In theory, you should constrain that to make sure that, for instance, it doesn't take more than 1 cycle of difference or that kind of stuff. I think that's the biggest limitation I encounter in the ECP5 and ICE40 tool chains.
Okay, well, thanks so much for your time, TNT.
Sure, no problem.
One of the great things about the open source tools is the community that's come up around them. And here I've collected some links for you to get started if you want to find out more. So what should you do if you want to give this a go and try it out? You should buy one of these recommended FPGA boards. I really like the Icebreaker. Esden over at 1-Bit Squared has done a great job with supporting and building the community, and his forum over at the Discord is a really fantastic resource full of great people. Orange Crab by Greg Davil is a very powerful board that you can run Linux on. And Black Ice is a nice offering from Folknology over in the UK, also with the Lattice FPGAs. Once you've got your FPGA, then to get started with Yosis and the open source CAD suite, you can download a Targi zip and just unzip this and run it. If you want to check out Xilinx support, then you'll need to use Symbian. So where are we going in the future? Let's take a look. Quality of results is improving, and we continue to squash more bugs even faster. More devices are being supported, and the ecosystem of tools and IP continues to grow. We also have a new foundation formed recently, the Open Source FPGA Foundation, and they are aiming to build new open source FPGAs from the ground up. And talking of building chips, we also have open source ASIC tooling now. So last year, the first open source PDK was released, and that gives us access to building completely open source chips from the ground up. So to conclude the presentation, let's take a little bit of a deeper look at the world of open source ASIC tooling. There's now an open source ASIC flow called OpenLane. To get the whole story, you should check out the FOSSI dial-up series of videos that was started by Tim Ansell, who's done a lot of work pushing both the FPGA and ASIC open source tooling. Google have sponsored 6 free shuttles. That's right, so if you make a open source design via eFabless, then you've got a chance of getting your ASIC fabricated free of charge. It's on 130 nanometers, working with the Skywater foundry based in the States, and you'd get 10 square millimeters. The next opportunity to do this is end of October for MPW3. And eFabless also offer the same thing for $10,000 and you get 300 chips instead of 50. So let's take a quick look at some examples of what people have been doing with this. Probably the most interesting for this audience is going to be Thomas Parry's satellite transceiver. I interviewed him over on my Zero to ASIC course YouTube channel, so you can get more info there. But he's building PLLs, ADCs, DACs, low noise amplifiers, transceivers, all open source and built on this 130 nanometer process. Another great initiative is the fabulous FPGA framework. This is being taped out on MPW2 and includes a practical example of 2 RISC-V cores with some FPGA fabric sandwiched in between. It's parametric and it's already supported by Yosys and NextPNR. So imagine what you could do if you put some radio systems right next to some FPGA fabric, right next to a RISC-V processor, and then put the whole thing on 130 nanometers. And now just to quickly plug my own project, the Zero to ASIC course, I'm doing this independently to teach people how to build open source ASICs using the current toolchain and get your device fabricated by eFabless as part of their Google open source shuttles. For MPW2, 14 people from the course put in their own designs, included things like cryptographic accelerators, graphics drivers, memory IP, and electromagnetic fault detectors. So that's the end of the keynote. I really hope you enjoyed it. If you want to check any of the links, then you can go here. And with that, let's see if we have some time for some Q&A.
And we do have some time for Q&A. The open source FPGA tooling has been something that has definitely been experimented with by various people in the community. And one of the things that seemed to be missing was an understanding of how the toolchain had evolved over the years. And so it's great to see the progress that's been made. And clearly we're getting to a point where it is possible to start considering this for designs, maybe not for your full commercial rollout right this year, but something to look at as it's coming down the line. And like we saw open source compilers really enable code in the early years, I'm definitely hoping that these sorts of tool chains open up a lot of innovation, and we're seeing that. So the FOSSI series of talks is also one I'd recommend. There's been a great series of content there over the last year. So we've got Matt's video.
How does licensing work with open source hardware? Does it impact the rest of my design? Does it impact my software at all?
I think that would depend a lot on the individual licenses of the IP that you were using. So you can separate out maybe the question in the license that we have on the tool and the tool chain where you're doing your synthesis and place in root, which probably doesn't matter what that is as long as it fits in with your business. And then the IP that you're going to be using is going to be completely dependent on the license of that IP, who's made it, and whether that's compatible with your business. So I'm sorry, that's a bit of a non-answer. Yeah, I highly recommend the Icebreaker boards from the 1-bit-squared community. And one of the big reasons behind that is the hardware's good, it's usually available, although it's been a bit more difficult recently, obviously. And it's supported by a great community, which is, I think, really important. The board's not so powerful and doesn't come with too much RAM, but the second link that I included in the presentation material from Greg Davil, there's the Orange Crab, and he's also got another one, the Butterstick, that has gigabit Ethernet and DRAM. So that's like a much more high-powered board. Also based on the ECP5, which is basically the best supported, most powerful FPGA we've got access to.
Great, thank you. I know that there's been some questions asked on the chat, and there's been answers fed there. So it looks like most of the people from the talk are hanging out in the chat at the moment. So if you have follow-on questions or would like to have direct conversations, they are there in the chat. I think
Yeah, I'll be hanging out there for the next 15 minutes if anyone's got other questions they want to talk about on offline.
Wonderful. Thanks very much, Matt. And I think that is us exactly on time, actually. So
Great.
Thank you very much, Matt. And we'll see you in chat.
Yeah, thanks very much.